In this video, we're going to talk about how the molecular structure of an acid can affect its overall strength, and a type of compound called an anhydride, which can form an acid or a base when placed into water. Right, so way back, when we talked about what made an acid, we talked about this thing called an acidic hydrogen. And an acidic hydrogen is a hydrogen that's involved in a fairly polar bond because it's attached to a region of fairly high electronegativity. Well, one of the ways you can strengthen an acid, especially a weak acid, is by increasing the polarity of the bond, right? So if you use a more electronegative element, the bond becomes more polar. Since the bond is more polar, it's easier to break off the proton than it would be otherwise, right? So more electronegative atoms can increase strength because it makes the bonds more polar. And by the way, this does work at a distance, so the hydrogen doesn't have to be directly attached to the very electronegative element. The electronegative element just has to be somewhere in the region. Now, I do point out that even though fluorine is the most electronegative element on the periodic table, HF is a very weak acid, not because of the polarity of the bond, but because the fluoride ion is really unstable because it has a full negative charge and it's a really small ion. Right? And another way you can increase the electronegativity or the polarity of the bond that hydrogen is attached to is you can add more oxygens, right? So more oxygens means more electron density is being sucked away from the hydrogen, which makes that bond more polar, therefore easier to break. Right? So one way you can increase the strength of an acid is to increase the electronegativity of what it's around. The other way to increase the strength of an acid is to have your conjugate base, your anion, be more stable. Right? So larger ions tend to be more stable than smaller ions are. That's, again, the reason why fluoride is unstable is because of how small it is. And if you can find a way to make resonance structures with those delocalized electrons are great at adding stability to an ion, and that will in turn make the acid a little bit stronger. Right, so we'll go over each of these kind of in turn. So we'll start off with electronegativity versus acid strength. So here we have a bunch of weak acids comprising elements of the second period. Right, so we have methane, ammonia, water, and hydrofluoric acid. Now, the thing to remember about pKa is that since pKa is negative log of Ka, is that lower numbers are more acidic. Right, methane has a pK of about 50. Not at all acidic, like really not acidic. Ammonia, a little bit more acidic because nitrogen is more electronegative. Water is more acidic than ammonia because oxygen is more electronegative. And HF is more acidic than water because fluorine is more electronegative. So we increase the electronegativity, we increase the acidity. This happens if it's directly bonded to hydrogen or if it's not directly bonded to hydrogen. So what we have here are different variants of acetic acid. Right? So electronegativity, its effect at a distance is called induction. So acetic acid pKa 4.75. If we put a bromine in place of one of the hydrogens out here, right, so this is CH3, so I'm just going to put CH3. If we replace one of these hydrogens with a bromine, notice how much stronger an acid it becomes. If we replace bromine with chlorine, it becomes slightly stronger. Replace chlorine with fluorine, still becomes slightly stronger. Right, so even at a distance, increasing the electronegativity of the molecule overall can pull electron density away from the oxygen-hydrogen bond, making it much easier to break. Now, oxygens can also cause an inductive effect, right? So perchloric acid is a very strong acid, right? 4 oxygens attached to this chlorine. All of this highly electronegative stuff is making this right here a very polar bond, very easy to break. And as we take away the oxygens, we very slightly decrease the overall electronegativity of the region, and this bond becomes slightly less polar, slightly harder to break, and same as we go down to 2 oxygens and 1 oxygen. Right, so the more oxygens you have, the stronger the acid will tend to be for any oxy acid. And ion stability, the 2 different ways to look at this. So ion size, H2O and H2S. H2S is a slightly stronger acid than water is because the sulfide ion is significantly larger. So that means that when it loses a proton and forms HS-, that ion is significantly more stable because of its larger size, larger volume to distribute that negative charge. And resonance forms, here we have acetic acid versus ethanol. Ethanol is a very weak acid because you can theoretically pull this hydrogen off, right? But because there's no resonance form for ethanol or for the ethanoate ion right here, to stabilize this negative charge, it's a fairly weak acid overall. Meanwhile, acetic acid, you can delocalize this negative charge among this region right here because this region experiences resonance. Right, so resonance can stabilize ions. That makes it easier to pull away the hydrogen because the anion is more stable. Right, so those are some different ways that you can affect the stability, or I should say the strength of an acid. And now we'll talk about something that they love asking multiple choice questions about, which are anhydrides. And anhydride, simply put, is when you dissolve it in water, it will form either an acid or a base depending on what it is. Your anhydrides are typically oxides, right? So if I take a metal oxide, like in this case sodium, and I dissolve it in water, it will form sodium hydroxide, right? So because it forms sodium hydroxide, this is a basic anhydride. It forms a base. Non-metal oxides form acidic anhydrides, right? So sulfur trioxide, when dissolved in water, will form sulfuric acid. Right, so anhydrides are oxides, whether metal or non-metal, that when you put them in water, will form either a base or an acid, depending on what type of oxide it is.